There are two other points to note about Lambert's projection. The first is that having brought the cone inside the Earth's surface, it was now necessary to mathematically adjust the graticule to keep the bearings correct. So the Lambert projection is orthomorphic, but non-perspective. Finally, notice that the constant of the cone has not changed. You can either think of the lower cone as being a smaller version of the upper one, or even as pushing an ice cream cone even further down onto the ice cream. The cone occupies a different position, but the angle at the top is still the same. This means that the convergence equation for the Lambert's chart is the same as for the simple conic. That is, chart convergence equals the change of longitude times the sine of the parallel of origin. Thus, the scale is correct at the standard parallels, but the chart convergence is determined by the parallel of origin. We are now going to consider all the important chart properties in the way that we did for the Mercator chart. This is our list, and we'll go through them one by one. The first of these is scale. Fortunately, we don't do any scale change calculations with the Lambert's projection, as we did for the Mercator. We just need to know that scale is correct on the standard parallels. In this area, it is expanding away from them. And in this area, it is contracting. The scale becomes least, or if you prefer, is most contracted, at the parallel of origin. Let's now consider orthomorphism. The chart is orthomorphic. All charts used for navigation must be. However, it is not rectangular. The meridians converge, but the parallels curve. When you put them together, they cut at 90 degrees. What about the graticule? Meridians are straight lines, originating from the pole. Parallels are arcs of circles centered at the pole. However, the pole is usually off the part of the chart which you are using. The size and scale of the chart determines how easy it is to see the convergence. For instance, on this Jeppesen North Atlantic Lambert's chart, which is on a scale of about 1 to 10 million, it is obvious that the meridians converge and the parallels are curved. Although, when using a half-million, such as this ED6, at first glance you might think that you were dealing with rectangles. The parallel of origin has one important property. It defines the chart convergence. Remember, the chart convergence factor, or n factor, is the sine of the parallel of origin. It is also halfway between the two standard parallels. This fact can be useful in solving problems. If you are given the two standard parallels, you can work out the n factor for yourself. In this example, the standard parallels are at 47 north and 43 north. This means that the parallel of origin must be halfway between them, in this case at 45 north. So the constant of the cone, or the n factor, is sine 45 degrees, which is 0.7071. The next one to consider is chart convergence. On the Earth, meridians converge, and the Earth convergency changes with latitude. But on the chart, the meridians are straight lines. So, if the left-hand meridian is paralleled over to the right-hand one, it makes the same angle, whatever the latitude. Therefore, unlike on the Earth, the chart convergence does not change with latitude. The equation is that chart convergence equals the change of longitude times the sine of the parallel of origin. Notice that this is not the same equation as for Earth convergence, which is the change of longitude times the mean latitude of the 2 points. And remember that the sine of the parallel of origin is often called the constant of the cone, or little n. How do Rhumb lines appear on this projection? Meridians are straight lines. All other Rhumb lines are concave to the nearer pole. And what about great circles? Except for meridians, which appear as straight lines, great circles appear as curves concave to the parallel of origin. A straight line in an east-west direction most nearly represents a great circle when drawn between 2 positions on the parallel of origin. Let's explain why. Imagine a spherical Earth, for instance, the real Earth or a reduced Earth. The meridians converge towards each other with increasing latitude. Now imagine 3 great circle tracks at different latitudes. In this example, we'll put them as 45 north, which is the parallel of origin, and at 47 north, and at 43 north. If you look down onto a great circle from directly above, so that the great circle is directly between your eye and the equator, it appears as a straight line. What will happen when we project this real Earth situation onto a Lambert chart, with a parallel of origin of 45 degrees north? The meridians straighten out. The projection causes the curved meridians to move outwards. What effect will this have on the great circle straight lines? The great circles will curve outwards as the meridians straighten. It looks like this. Great circles form a straight line at the parallel of origin, and are curves concave to the parallel of origin at other latitudes. However, a word of warning. The amount of curvature is exaggerated in these diagrams, simply to make the explanation clearer. In fact, there is very little curvature compared with a straight line, and for all practical purposes, including plotting, great circles on a Lambert's chart may be treated as straight lines. So, let's summarize what we have covered. We looked at scale. It is correct on the standard parallels. It contracts inside them, becoming least at the parallel of origin. It expands outside the standard parallels. The chart is orthomorphic. All charts used for navigation must be. The graticule is fairly straightforward. Meridians are straight lines originating from the pole. Parallels are arcs of circles centered at the pole. The pole is usually off the page. The parallel of origin determines the chart convergence. It is the mathematical basis of the projection. It is assumed to be halfway between the 2 standard parallels. We say assumed because we use this as a given fact for all exam calculations. In fact, because of Lambert's adjustments, it is not perfectly in the centre, but the difference is negligible. The chart convergence is constant across the chart. The equation is that chart convergence equals the change of longitude times the sine of the parallel of origin. How Rhumb lines are shown depends on their orientation. Meridians are straight lines. However, they are the exception. All other Rhumb lines are concave to the pole. This is most easily visualized by considering a parallel of latitude. And finally, great circles. Meridians are straight lines. The parallel of origin is considered to be a straight line. At any other latitude, a great circle is a curve concave to the parallel of origin. That concludes this first lesson on the Lambert chart. The next lesson will consider how these properties affect the way that we use it.